optimization of passive vehicle suspension system using genetic algorithm. So first thing is why we have chosen optimization is required for maximization or minimization of any condition. So here we are using optimization for maximizing the ride comfort. I'll later on explain the term ride comfort. So this is optimization. And why we have chosen passive vehicle suspension system? Because passive vehicle suspension system is widely used in automobile industries and in commercial vehicles. So if research is done on passive vehicle suspension system, it will be helpful on large scale. And the next thing for the optimization, there are many techniques, but with some advantages of genetic algorithm, we have chosen the genetic algorithm technique for optimization purpose. So what are the basic functions of suspension system? First thing is to isolate the vibrations that are transmitted from road irregularities to the human body and the vehicle. So that is the isolation of vibration. Then the next function of suspension system is passenger comfort, and also to carry the weight of the vehicle structure and also the human body mass. Then the next function is to maintain the contact of wheels with respect to road surface. The term for it is the road holding. We call it as the road holding. The basic motto of the project or the literature is why suspension system, because there are semi-active and active suspension systems also used in automobile industries. But the basic focus on passive suspension system is done, as I said, is due to this suspension system is widely used in all the commercial vehicles, and mostly 90% of the vehicles use passive suspension system. So the research on this would be more beneficial, and even in passive suspension system we can achieve a good ride comfort and also good road holding by doing some kind of good optimization in this research topic. Now the basic terms in suspension. There are two basic terms in suspension. First thing is ride comfort, that is called RC, and the ride comfort is measured in terms of sprung mass acceleration. And the sprung mass acceleration is obviously the RMS acceleration meter per second square. And I can say that if sprung mass acceleration is minimum, then the ride comfort is maximum. So this is how they are correlated. They are inversely proportional. The next thing is road holding. Road holding is relative displacement of tire with respect to road. So road holding, I can say road holding is good when the vehicle maintains good contact with the road surface. So road holding and relative displacement is also inversely proportional. That is, if relative displacement is more, then I can say road holding is less. And you can see from the graph here that road holding and ride comfort are contradictory in nature. That is, if one increases, then the other one decreases. By ISO 2631197, the conditions are defined as if the RMS acceleration is less than 0.315 meter per second square, then the discomfort level is not uncomfortable. So if we achieve the value less than 0.315 meter per second square, then we can say that we are in comfort zone. So the outlines of the projects are, the first thing is done is the derivation of objective function. This we have done for quarter car model. Then the mathematical models was built up from the basic quarter car model. We have also built a mathematical model for quarter car with a driver seated on a driver. That is quarter car with thorax and pelvis. And another is simulating. Then the simulating models were built up. Using the same mathematical model, we have built simulating model for both conditions. Then the next is validation, because once we build up the models need to be verified whether they are correct, so that the further research can be done. So the validation was done, and then the optimization was done by using genetic algorithm technique. And then these optimized values were then put into simulating model, wherein we can get the required results. So this is the objective function of quarter car. So we can see the two equations, RC and RH. RC is ride comfort, and the next is RH is road holding. These two equations are for basic quarter car model, and these are these equations are obtained by model analysis, which was entirely coded in Matlab software. And the parameters here, sigma and gamma, these represent a part of equation. Since the equation was too large, we have represented part of equation by gamma and sigma. So after we get the objective function for quarter car, then we move to the mathematical model. So this is the basic quarter car model. So you can see the sprung mass, unsprung mass, and the K is spring stiffness, damping coefficient, and KT is tire stiffness, and the Z is the displacement corresponding to the masses. So once we build the mathematical model, from the FBD we can get the equations of motions. So for quarter car we get two equations of motion, and for this with a driver seated on a driver we get four equations of motion. So the next thing is, after we build the mathematical model, from these equations of motions we can build the simulation models by using the equations of motion in Matlab simulating software. And the simulation models are for both. This is for quarter car model, and the next one is for quarter car with driver seat. This is with thorax and pelvis, that is quarter car with driver seat, driver seat and on driver seat. Also the experimental model was built by another group. So from this we have taken the results to verify our model, because the simulating model and theoretical model can't be used until and unless they are verified with the experimental model, that is test tree. So this was developed by another group, and the results we achieved, then we compared it to use. Now the verification of model will be explained by my colleague Saaish.
So these three models, how we have verified is shown here. What we have done is we have given same input conditions to all the three models, and we have calculated the outputs from the three models, and we have calculated correlation index. This is the formula for correlation index shown here, and as you can see, the above table shown is with correlation index above 0.85. So we can say that the three models are well correlated. So here also here two surface plots are shown. This is for experimental model and this is for theoretical model. These two surface plots are nothing but RC versus spring stiffness and damping coefficient. As you can see the similarities, we can say that these three models are correlated, and we can now use optimization of theoretical model, and we can use that results into simulation model. Next one, we have to give input road excitation to the simulation model, that we are using half wave sine bump here. Then optimization, we are using genetic algorithm because of some of its advantages, like it's a large size of population, then they do not need continuous functions, and also these are probabilistic search techniques like that. And here is simple algorithm shown here. We are using large size of population, and we are evaluating the function using objective functions we have. Then these are the three GA operators. In reproduction, we can identify which are the good solutions we have to carry on, and we can identify the bad solutions that we have to eliminate. And in crossover and mutation, we can generate the new different solutions. Reproduction cannot generate new solutions. So after iterating these three operators continuously, we can generate a large number of output solutions, and among that we can select the best fitness value for our result. So next one, as we have two objective functions, one is RC and one is RH, we are using multi-objective optimization. We are using Matlab software toolbox named genetic algorithm here. It shows the output like Pareto chart, where you can see on x-axis you have one objective function. Here it is RC, and in y-axis it's RH. Actually, in fact, on x-axis it is sprung mass acceleration, and on y-axis it is relative displacement. So this point indicates best RH in the vehicle, and that point indicates best RC in the vehicle. And these all are totally optimized points, and we can select any one point for whatever according to our requirement. So this point indicates the case where road holding is maximum, that means it's sports car, and this point indicates the results for luxurious cars. So in our taking the results from simulation, we are using luxurious cars, so we are using this point as our best optimized point, and we are doing analysis in the simulation further. This is the result shown here. Then these two sets of parameter values we have here, before optimization and after optimization. We are using these two values in the simulation model, and we are checking out whatever improvement we are getting. So the further results will be explained by Gaurav.
So once we get the results from the optimization, that's by genetic algorithm, all the 5 parameters, spring stiffness, damping coefficient, sprung mass, unsprung mass, and tire stiffness. Once we get these results, now we have a set of parameters, before optimization parameters and after optimization parameters. Now these parameters we can give as an input to the simulating model, and then the results we get output, we can compare those before optimization and after optimization. And we can see that what was the percentage change, have we achieved the required values. So this was for sprung mass acceleration. You can see here that before optimization is the red one, and after optimization is the blue one. So we have got the ride comfort, increase in ride comfort by 13.3%, and also the damping time is less, and also the amplitude is less. after optimization. Now the next is road holding. As I said that both are contradictory in nature. If one increases and the other one decreases, then you can see here that the road holding is decreased by -3%, but the ride comfort is increased by 13%, and the values are below zero. It states that the compression, static compression of the tire. The next thing is the driver head acceleration. This the overall RMS acceleration is the ride comfort is decreased by -0.3%. This is due to the increase in amplitude, initial increase in amplitude. If you can see the after optimization, here, the blue graph, the amplitude is more than before optimization. So due to this, the value is decreased, the ride comfort is decreased. But if you see the amplitude, the drastic change in the amplitude, then after optimization, the amplitude, the damping is quite good than before optimization. So the conclusion is that by using the genetic algorithm, the different parameters regarding the suspension system before optimization and after optimization was compared, and we achieved the ride comfort level to 13.3%, increase in ride comfort by 13.3% with much less decrease in road holding by 3%. And so these are the references used. Thank you. Any questions?